Yeah, I will be talking to you today about energy storage, because it's a topic that has been mentioned at the start of the day as being quite important to allow the transition to renewables. And in particular, I'll be talking about a technology called compressed air energy storage and using it in porous rocks. So you probably all have in your pocket a battery right now, but there is quite a lot of complexity in the challenge of energy storage. And one of them is the time dimension. So why do we need interseasonal electricity storage? So more and more research suggests that when we have over 80% of electricity that is produced from renewable energy sources that are variable or other sources that are not easy to fluctuate, let's say, then we will have a serious need for interseasonal storage, and maybe even before that. Most of the current research and work, however, is focused on short-term storage. So this is understandable because that's one of the things that we currently need right now and in the near future. But I think we should be careful not to forget what lies on the horizon. So why compressed air? I'm not sure if you ever heard of this technology before. And if you have, it was probably in passing. You probably heard about hydrogen and blue hydrogen with methane. But I think those are more suited for the challenges of heat and transportation. So compressed energy storage was found to be a good candidate because when you use it to convert electricity and back to electricity, it's actually more efficient than doing it using hydrogen. So I'm aware this is a gross cartoon, but it essentially illustrates the concept of the technology. So during the summer, we could use excess electricity to compress air into a reservoir. And during the winter, we can take this air back out again, expand it through a gas turbine to generate electricity. This is a very conventional technology in terms of it's already been used before. It uses off-the-shelf components, an air compressor and a gas turbine. The gas turbine currently uses natural gas, but it could also use hydrogen, and other alternatives are being studied to remove the need to combust a gas during the expansion. The efficiency of that system is around 60%, and there are currently 2 plants worldwide that use this technology on a daily cycle. So now that you know a bit more about this technology, I want to put it in the context of sustainability in the energy transition. So one definition of sustainability that was given by the United Nations is that it's the ability of today's generations to meet their need without preventing future generations from doing so themselves. And this concept, this understanding, relies on 3 broad pillars. The first is preserving the environment. The second is on social equity, and the third is on economics, because whatever you do needs to be viable economically. I think that compressed energy storage can contribute quite a lot to all of those pillars. The first, by contributing to decarbonizing. And by that, I mean making renewables dispatchable, allowing them to perform better, increasing their value. So storage is expensive, but if you're considering what it does for the energy transition, I think it has a lot to bring. Secondly, I also want to mention the fact that I said it was using natural gas. But because you're actually compressing your air using renewable electricity, the amount of CO2 emissions per kilowatt hour that you get out of that system is much lower than it is for a conventional gas turbine, where almost 2/3 of the energy is actually spent on compressing the gas before burning it. The second pillar is social equity. So I think here, and it's more in the context of geosciences generally, but it's really an area where past knowledge and the current workforce has a role to play in educating us, the younger generation, and also working with us to achieve the energy transition. So in that respect, both the current workforce and the future ones need to work together to achieve the energy transition. Another important aspect, which is maybe more relevant to compressed air energy storage, is the fact that it increases the affordability of energy from renewables by bridging the gaps and limiting the swings and the fluctuations in prices over the year. And finally, I'm going to talk about this a bit more in the rest of the talk, but how could we reuse the geological assets and the topside assets of technologies to build a sustainable future? So what do I mean by that? Currently, we've seen a massive increase in natural gas, and wind and other renewables are starting to pick up, and they're becoming really cheap. So if we start using CCS now, we've seen that it's risky. We need to know a lot about the subsurface, and this is going to cost a lot of money. So if we do this initially for CCS, it seems a bit redundant to do it all again when you start needing compressed air energy storage, because the renewables are going to keep increasing. So could you potentially use all that knowledge and that investment that you've put into understanding the subsurface for carbon capture and storage into building compressed air energy storage? And that is not a brand new idea, but the idea is to say you could, if you have a decent structure, you've used it, you've filled it up with carbon dioxide, and you start injecting air. The air is more buoyant, and you're essentially going to have an air cap that you can now use as your standard compressed air energy storage system. So I think thinking of all those kinds of technology, whether that's carbon capture and storage, compressed air energy storage, hydrogen storage, we need to start as geoscientists to look at all those technologies together and see where the links are and where the benefits are to make all those expensive technologies more readily affordable. So in conclusion, I would say keep in mind the 3 pillars when considering a technology for the energy transition. Identify the interactions between those technologies as early on as you can. And that is going to involve going to talk to other people, other geoscientists, but also now we need to start taking our head out of the ground a bit and go and talk to network engineers and industry experts to understand how exactly we can couple our subsurface technologies to the wider energy network, especially if you use technologies like compressed air energy storage, which are going to provide a power service, or hydrogen storage that can provide fuel for the decarbonization of heat, for example. And thirdly, but not last, we need to start thinking now about the commercial and regulatory regimes that we want in place to enable us to capitalize on those technological interactions that I've mentioned. Over the past year, I've noticed that this is not straightforward. Okay, it's not because you're allowed to operate a CCS that you will be allowed to operate a compressed air energy storage plant or a hydrogen storage site. So we need to make sure that all this is in place to allow the transition to happen. If you want more information on the technology of interseasonal compressed air energy storage, I refer you to this paper that was one of the outputs of my PhD. Thank you very much for your time.